In this video, we're going to be talking about optimization problems. So most of these come from word problems. There may be some geometry type situations or some graph situations, but a lot of the time it's an application. So this is a kind of a classic example. It says you run a successful dog sitting service and you have determined that you need to construct a new dog run in your backyard. To save money, you plan to do the work yourself and to fence an area adjacent to the side of a building. According to your budget, you can afford to buy materials to build 26 feet of fencing. What dimensions will give you the largest area for the dogs to play in, and what is that area? So this type of problem is what we call an optimization problem. For these types of problems, there's always a quantity which must be optimized. In other words, we need to either find the maximum or the minimum value for the formula of that quantity. So this formula is what we call the primary equation. So for this particular problem, if we want to find the primary equation, it might help to draw a picture and label our variables. So we've got a building, and if we're going to build a fenced-in yard adjacent to a building, that means one side of the yard doesn't need fencing. So we're going to draw kind of a rectangle coming off of this building right here. Okay, so I'm going to label this side as X, and of course they're the same because it's a rectangle, and this side is going to be Y. So the primary equation here is that we are trying to maximize our area, which would be X times Y. So that's our primary equation. Now, optimization problems typically include another piece of information which is going to help you form what we call a secondary equation. So if we want to find the secondary equation for this problem, we look back to the word problem and see what's limiting us. Well, in this case, what's limiting us is the amount of fencing that we can build. It says we can afford to buy materials to build 26 feet of fencing. So I've got three sides which have to be equal to 26. So the length of the fencing would be equal to 2x plus y, because I only need one side of y, and that has to be 26. So 2x plus y equals 26 is my secondary equation. So we know from section 3.1 and 3.3 how to find absolute extrema of a function on a closed interval, or relative extrema depending on the problem, as long as that function is of a single variable. So our function a equals xy is not of a single variable, but we can use our secondary equation to force it to be. So I'm going to take my 2x plus y equals 26 and solve it for y. And I'm going to take that a equals xy, which was my area, and substitute. So that'll be x times negative 2x plus 26, or negative 2x squared plus 26x. So that's going to be my function a of x that I'm going to use. Now, since these are application problems, our answers do need to make sense in the given situation. So that means that we need to find what's called the feasible domain of our problem. So in this case, our feasible domain says that, you can't have negative fencing. So we know that x has to be greater than or equal to 0, and y has to be greater than or equal to 0. Okay, so let's just assume that we've got y equal to 0. I know that's ridiculous, you wouldn't do that, but we're trying to find some limitations here for x. If y is equal to 0, that means all of the fencing gets used on x. So negative 26 is negative 2x, or 13 is equal to x. So that tells me my feasible domain is that x has to be between 0 and 13, or the interval from 0 to 13. So now that we know what those bounds are, we're actually using calculus to find the optimal dimensions. We're trying to find the absolute max area, a equals negative 2x squared plus 26x, which we found up here, on the closed interval from 0 to 13. So this has become a 3.1 problem at this point. So I'm going to find the derivative. A prime of x would be negative 4x plus 26. If you set that equal to 0, you get that 4x equals 26. And if you divide by 4, you get that x is 26 over 4, which is 6.5 feet. Now that gives you x. Now this is an application problem. Normally when you go to find the y value of a problem, you end up you end up finding a prime at that value. But if you actually found, a at that value, but if you actually found a of 6.5, that's going to actually give you the area. It's not going to give you the y value. So that's going to end up being that's going to end up being negative 2 times 6.5 squared plus 26 times 6.5, which ends up being 84.5 feet squared. So that's the area, but we do need to find y. So remember, y was negative 2x plus 26, which would be negative 2 times 6.5 plus 26, or negative 13 plus 26, which is 13 feet. So the largest area you can fence is 84.5 feet squared with dimensions 6.5 feet by 13 feet. And you can absolutely check, multiply 6.5 times 13 and make sure you actually get the area that you were expecting. So you can see the process that we've gone through. We first want to identify everything we're given and everything we want to find. You might need to make a sketch. We want to write our primary equation. We want to write our secondary equation. Use the secondary equation to put the equation into one variable and find the feasible domain. And then you want to solve it using the calculus that we've learned so far. So this is a classic example. We want to find two positive numbers such that the sum of twice the first plus the second is 18, and the product is a maximum, and we want to know what is that product. So first of all, I'm going to let x equal the first number, and I'm going to let y equal the second number. You could say that x is the larger number if you want to. Our primary equation is that we want to maximize the product, which is xy. Our secondary equation comes from the statement that the sum of twice the first number plus the second is 18, so that would be 2x plus y equals 18, or y equals negative 2x plus 18. So if I were to plug that in, p is xy, which is x times negative 2x plus 18. So I get that p of x is a function negative 2x squared plus 18x. My feasible domain, I know that x has to be greater than 0 and y has to be greater than 0 because they're two positive numbers. So if I were looking for a bound, if y was equal to 0, then 2x plus 0 would be 18, so x would be equal to 9. So that's my upper boundary for x. So I know that x has to be between 0 and 9. Now this is not a closed interval, so if you don't have a closed interval for your feasible domain, then you actually are going to have to find relative extrema and use one of the tests that we have for that. So in this case, I'm going to find p prime of x, which is negative 4x plus 18. It exists everywhere, so if I set it equal to 0, I get 4x equals 18, or x equals 9/2. Okay. Now, again, this is not a closed interval, so I'm going to actually use the second derivative test just to verify that this is actually a maximum. So I'm going to find the second derivative, p double prime of x, which is negative 4, and since that's less than 0, any critical number is a relative max by the second derivative test. Okay, so my numbers then, I know that x is equal to 9/2 or 4.5, so y would have to be negative 2 times 9/2 plus 18, or 9. So my numbers are x equals 9/2, y equals 9. My product I could just find by multiplying the two, which is going to be 81 over 2. So that is my answer. Now in this example, we want to find the point of the graph of f of x equals x squared that is closest to the point 2 comma 1/2. So when we're talking about closest, we're talking about distance. So I'm going to let this be x of 1, y sub 1, and I'm going to let x of x comma y, which we'll call x2, y2, be a point on the graph of f of x equals x squared. Okay? So my primary here is that I want to minimize the distance. So that's d equals the square root of x of 2 is x, x of 1 is 2, so x minus 2 squared, plus y minus 1/2 squared. So that's going to be my primary equation. My secondary equation actually comes from the graph. I have that y is equal to x squared. So when I put these two together, I get that d is equal to the square root of x minus 2 squared plus x squared minus 1/2 squared. And I'm going to just expand that, so I get x squared minus 4x plus 4 plus x to the 4th minus 2 times 1/2 times x squared, so that's minus x squared plus 1/4, or the square root of x to the 4th minus 4x plus 17 over 4 is what that reduces to. So I could make this the square root of u, where u is equal to x to the 4th minus 4x plus 17 over 4. So when I go to find the derivative with respect to x of d, this would be u prime over 2 square root of u. U prime here is 4x cubed minus 4. So this is going to be 4x cubed minus 4 divided by 2 times the square root of x to the 4th minus 4x plus 17 over 4. So in this case, I can cancel the 2 with all three of these. So I get 2x cubed minus 2 divided by the square root of x to the 4th minus 4x plus 17 over 4. Now the feasible domain for this problem, if you were coming back to look at that, would be any point where x is, or sorry, any x where x to the 4th minus 4x plus 17 over 4 is greater than 0. So you got to think about that, because if it was equal to 0, it would be the same point, so that wouldn't really count. So it's got to be greater than 0. So the only point that makes the derivative not exist is actually not in the feasible domain. So we're only concerned about where it's equal to 0, and that's when 2x cubed minus 2 equals 0, or if you do the work, you get that that's when x is equal to 1. Now in this case, I'm going to find the first derivative, or I'm going to use the first derivative test. I could have possibly used the second derivative test here, but honestly, using the first derivative test is easier than trying to find f double prime of x for this function. So I'm going to choose the path of least resistance. So my intervals would be from negative infinity to 1, from 1 to infinity. I could pick test points at 0 and 2. I would find the second derivative. So if I plug 0 in, I'm going to get a negative number. If I plug 2 in, I'm going to get a positive number. So the fact that we are decreasing and increasing here means that this is a relative minimum. And at x equals 1 is relative minimum, so y would be equal to f of 1, which would be 1 squared, or 1. So the point closest to the graph of f of x equals x squared, or closest to the point 2 1/2, on the graph of f of x equals x squared is the point 1, 1, and that is my answer. This is another example of something you might see. We have a rectangle that's bounded by the x-axis and the semicircle y equals the square root of 64 minus x squared. What length and width should the rectangle have so that its area is a maximum? Now this is important. When you look at this, you're tempted to let the width be x and the height be y, but that would actually be incorrect because this distance right here is actually x. So if you plotted the point here, this would be the point negative xy because it also has a distance of x. So the width here of this rectangle is actually 2x and the height is just y. So my primary equation is to maximize the area, which is 2xy, and my secondary equation is the circle, or the semicircle, y equals the square root of 64 minus x squared. So my feasible domain, we can find out pretty quickly, is that x has to be in the first quadrant, but it's got to be on the circle, which goes through 0, 8, or yeah, through 8, 0. So x has to be in the interval from 0 to 8. And that is a closed interval, so in this particular problem, we could potentially use the 3.1 process of finding extrema on a closed interval. So I am going to go ahead and plug this in. So I'd have area A of x would be 2x times the square root of 64 minus x squared. Okay. I want to find the derivative. I'm going to have to do that using the product rule. So a prime of x, when I go through the derivative using the product rule, ends up being negative 4x squared plus 128 over the square root of 64 minus x squared. So I'm going to find out where this doesn't exist or where it's equal to 0. So a prime of x is equal to 0 when negative 4x squared plus 128 is equal to 0. So 4x squared is 128. Or x squared is 32. So x would be, in this domain, the square root of 32. We don't need the plus or minus because it's not negative. Negative would be over on the other side. And in this case, a prime of x does not exist, where 64 minus x squared equals 0, or x equals 8 in this domain, which this is an endpoint, so we're going to test that anyway. No big deal. Okay, so we need to compare our y values. So a of 4 square root of 2 would be equal to 2 times 4 square root of 2 times the square root of 64 minus 4 square root of 2 squared, which simplifies down to be 8 square root of 64, or 8 times 8, which is 64. If we found a of 0, we would have 2 times 0 times the square root of 64 minus 0 squared, which is 0, and a of 8, which would be 2 times 8 times the square root of 64 minus 8 squared, or 0 as well. So we can verify that this is the max. We do need to find y. So y would be the square root of 64 minus, I'm just going to go back to that root 32 just for convenience. So that's the square root of 64 minus 32, or the square root of 32, which is also 4 root 2. So my answer is that the length is going to be y, which is 4 square root of 2, but the width of this rectangle is going to be 2x, which actually ends up being 8 square root of 2. So that is my answer. Make sure that you answer all the questions. In this case, it doesn't actually ask what the maximum area is, but if it did, you would want to put that down as an answer as well. So those are optimization problems. Now you do have a set of extra problems for you to work. These are on Blackboard, and the solutions to these will be on Blackboard as well. So I'm not going to make a video for these, but they'll be written out for you.